Yeah. We only need to go
Thank you
through.
all for attending.
Oh, what are you saying?
What was that, Kai?
Let's go through the. Actually, we should. How many? Oh, this is 44 pages. Sheesh.
I'll skip the highlights.
No,
a lot of it will be explanations of the testing, and this paper is fairly image heavy as well.
Well, ideally, like we should kind of go over the history. This is like important. Yeah, let's just go over it.
Let's try and get as far as we can.
Yep.
Okay. This is a paper from December 2022. What do vision transformers learn? A visual exploration from Amin Gaji, Hamid Kazmi, Etienne Borgna, Steve Reich, Manly Shu, Micah Goldblum, Andrew Gordon Wilson, and Tom Goldstein from University of Maryland College Park and NYU. Vision transformers, VITs, are quickly becoming the de facto architecture for computer vision, yet we understand very little about why they work and what they learn. While existing studies visually analyze the mechanisms of convolutional neural networks, an analogous exploration of VITs remains challenging. In this paper, we first address the obstacles to performing visualizations on VITs. Assisted by these solutions, we observe that neurons in VITs trained with language model supervision, for example, CLIP, are activated by semantic concepts rather than visual features. We also explore the underlying differences between VITs and CNNs, and we find that transformers detect image background features just like their convolutional counterparts, but their predictions depend far less on high-frequency information. On the other hand, both architecture types behave similarly in the way features progress from abstract patterns in early layers to concrete objects in late layers. In addition, we show that VITs maintain spatial information in all layers except the final layer. In contrast to previous works, we show that the last layer most likely discards the spatial information and behaves as a learned global pooling operation. Finally, we conduct large-scale visualizations on a wide range of VIT variants, including DEIT, COAT, CONVIT, HIT, SWIN, and TWIN to validate the effectiveness of our method. Introduction. Recent years have seen a rapid proliferation of vision transformers across a diverse range of tasks, from image classification to semantic segmentation to object detection. Despite their enthusiastic adoption and the constant introduction of architectural innovations, little is known about the inductive biases or features they tend to learn. While feature visualizations and image reconstructions have provided a looking glass into the workings of CNNs, these methods have shown less success for understanding VIT representations, which are difficult to visualize. In this work, we show, if properly applied to the correct representations, feature visualizations can indeed succeed in VITs. This insight allows us to visually explore VITs and the information they glean from images. And figure 1. The progression for visualized... Can you scroll down a little bit, please, V?
Tick tock, tick tock, tick 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 tock, tick tock, tick tock, tick 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 tock.
Hello, V. Could you scroll down a little bit, please?
He fell asleep. Yo, wake up, V. Plenty. Can you take the mantle here? I have a fallen soldier.
A sleeping soldier.
Probably like yo yo yo. Yeah,
Let's
he's
go,
gone.
V.
Yeah,
Oh boy.
he's gone. Short attention spans will
We
get you.
love you, V. It's really late where he is.
Yeah. Plenty, can you take up the mantle?
Yeah.
Thank you, Plenty.
Let me pull it up.
He was literally here for like 2 seconds.
So the interesting thing about this paper for me is that it learns semantic and spatial features rather than only purely visual ones. But that's true of any.
Yo, is it fixed? Alright, Plenty, did you get it up?
Yeah, I'm downloading the PDF right now. The computer's lagging a bit because I'm running the agent. Okay.
We're just about ready for figure 1 at the bottom of page 1. Thank you, Plenty. A little bit up from that, please.
Oh, figure 1, page 1.
Yes, thank you. That's it. The progression for visualized features of VITS B32, features from early layers capture general edges and textures. Moving into deeper layers, features evolve to capture more specialized image components and finally concrete objects. From left to right, we have edges, textures, patterns, parts, and objects. Have kind of a deep dream quality to this figure. And at the top of the next page is figure 2.
Let's see this. Ooh. Let's analyze this. So, edges, textures, patterns, parts, objects. Oh, wait, let's go back to figure 1. We need to go deeper into these visualizations. Can't just pass them. Can you go deeper, Plenty? Go deeper. Yes.
So edges and textures are fairly standard signal processing filters.
So
Patterns,
features from
objects
early layers capture
not-
edges. Deeper layers, features evolve to capture more specialized image components. So early layers capture edges, textures. Deeper layers, they learn patterns and parts and objects. And it always looks like they're on psychedelics.
Yeah. So how many layers would a VIT model have?
It depends. basically just the number of heads, or I mean, like the deaf. So quite a bit. But layers can mean anything. They can mean like attention heads, transformer blocks. Like it's not very specific. There are multiple layers.
Yes. So I guess my question is, are we talking, if they're describing layers as detecting edges versus objects, are we talking about 5 layers, or are we talking about 500?
No, definitely not 500. Definitely not 500. Let's just keep going on. Let's figure that out. Because like I said, there's multiple layers of different things. And my brain doesn't...
trying to get an idea of how many different things they're attempting to capture with the transformer model.
Yeah. Like I said, it can mean multiple things. I need precision. I don't, without precision, I don't know what the hell they're talking about. So we're gonna find out.
Figure 2, which is appropriate for Halloween. Features from bits trained with clip that relates to the category of morbidity. Top left image in each category. Image optimized to maximally activate a feature from layer 10. The rest, 7 of the 10 images that most activate the feature.
Can you scroll up deep into the first one? Yes. Yeah, that is pretty crazy. That's really horrifying. Shit. What are you thinking? How does this work?
The first one.
Can you go back up, please? Can you go deep into the first one? Go very deep. Like very, very, very deep. Yes, very deep. Deeper. So it's capturing the texture and the objects. It's capturing the edges.
Also, there's kind of a positional thing. There's a spatial relation it's capturing.
Can you go right? Go right, Plenty? Yeah, go right a little bit. So that's Day of the Dead. That's tomorrow. Yeah, those are dead people. Well, not really people, dead toys, but they represent dead things. The church, yeah, those people are not here anymore. That person is still alive. They're just dressing up dead. You could see how some of these things are fake. Like that person isn't dead. What was the question again? Was it dead? Dead people? Morbidity. So that is much more general than dead people, which is what I thought it was.
Yeah, a lot of those images are Halloween.
Yeah. All right, let's keep going.
Thank you, Plenty. In order to investigate the behaviors of vision transformers, we first established a visualization framework that incorporates improved techniques for synthesizing images that maximally activate neurons. By dissecting and visualizing the internal representations in the transformer architecture, we find that patch tokens preserve spatial information throughout all layers except the last attention block. The last layer of VITS learns a token mixing operation akin to average pooling, such that the classification head exhibits comparable accuracy when ingesting a random token instead of the CLS token. And that maps into a paper we read last week about SAMClip, in which they used a pooling layer at the end to merge a segmentation learning model, SAM, and a clip learning model as a VIT. After probing the role of spatial information, we delve into the behavioral differences between VITs and CNNs. When performing activation maximizing visualizations, we notice that VITs consistently generate higher quality image backgrounds than CNNs. Thus, we try masking out image foregrounds during inference and find that VITs consistently outperform CNNs when exposed only to image backgrounds. These findings bolster the observation that transformer models extract information from many sources in an image to exhibit superior performance on out-of-distribution generalization, as well as adversarial robustness. Additionally, convolutional neural networks are known to rely heavily on high-frequency texture information in images. In contrast, we find VITs perform well even when high-frequency content is removed from their inputs. I apologize, please. Could you mute? While vision-only models contain simple features corresponding to distinct physical objects and shapes, we find that language supervision in CLIP results in neurons that respond to complex abstract concepts. This includes neurons that respond to visual characteristics relating to parts of speech, for example, epithets, adjectives, and prepositions, a music neuron that responds to a wide range of visual scenes, and even a deaf neuron that responds to the abstract concept of morbidity. Our contributions are summarized as follows. First, we observe that uninterpretable and adversarial behavior occurs when applying standard methods of feature visualization to the relatively low-dimensional components of transformer-based models, such as keys, queries, or values. However, applying these tools to the relatively high-dimensional features of the position-wise feed-forward layer results in successful and informative visualizations. We conduct large-scale visualizations on a wide range of transformer-based vision models, including VIT, DIT, POT, Convict, PIT, SWIN, and TWIN, to validate. Number 2, we show that patch-wise image activation patterns for VIT features essentially behave like saliency maps, highlighting the regions of the image a given feature attends to. This behavior persists even for relatively deep layers, showing the model preserves the positional relationship between patches instead of using them as global information stores. Wow. And number 3, we compare the behavior of VITs and CNNs, finding that VITs make better use of background information and rely less on high-frequency textual attributes. Both types of networks build progressively more complex representations in deeper layers and eventually contain features responsible for detecting distinct objects. Number 4, we investigate the effect of natural language supervision with CLIP on the types of features extracted by VITs. We find CLIP-trained models include various features clearly catered to detecting components of images corresponding to caption text, such as prepositions, adjectives, and conceptual categories. I'm going to skip ahead to see if we want to read the next section.
Ideally, for a paper like this, it would be very advisable to read the whole thing. Kind of like how you want more reasoning tokens. Um, yeah, ideally you want as many reasoning tokens as possible. Like I'm talking about you as a person. Um,
I disconnected. Could you start that again, Kai? I missed the beginning.
yeah, so ideally you like in a situation like this where you know basically nothing about the history of the VIT class, or like not VIT class, the VIT model. You want to learn as much about the history in the past, like this is a type of paper where you read the whole thing in full.
Okay.
I'm not saying we need to read the whole thing in full. I'm just like letting you know, like it would most likely be advisable.
Yeah, correct. This is a well written and detailed paper, and they have done a good investigation of related work.
Yeah.
I skipped this mostly for time.
Yeah.
Pliny, would you mind scrolling down to section 3? Thank you. And a little bit up from there. Yeah. VIT feature visualization. Like many visualization techniques, we take gradient steps to maximize feature activations starting from random noise. To improve the quality of our images, we penalize total variation and also employ jitter augmentation. The color shift augmentation and augmentation ensembling. Finally, we find that Gaussian smoothing facilitates better visualization in our experiments, as is common in feature visualizations. So let's take a look at figure 3. It's one I think is going to need a bit of a zoom. Figure 3A. Example feature visualization from the VIT feed forward layer. Left. Image optimized to maximally activate a feature from layer 5. Center. Corresponding maximally activating ImageNet example. And right, the image's patch-wise activation map. B, the feature from the last layer most activated by shopping carts. So, do you understand what's going on in the left image there? Like left A?
Let's go up. Go up a little bit, please. Okay, now go on the first one. Or go back a little bit. We need to read the caption.
So the left image is designed to maximally activate a feature from layer 5.
So that is. Can you go back out, Plenty? Go back out all the way, so we can read the caption, the full caption. So example feature visualization from a VIT feed forward layer. Whoa.
We've got ghosts plenty.
Okay. Sorry, guys. I don't know what happened. Maybe I'll take that as my cue to get some sleep, though. Can someone take over for me?
Sure.
I will attempt to keep going. Thank you plenty. Have a good night.
Thanks, guys. See you tomorrow. Good night.
Good night. All right. I'm gonna be sharing my screen because everyone else seems to be asleep.
Thank you, Kai.
Sleepyheads. just a sec. Alright, so what where are we located?
We're
Yeah.
at the top of page 3, I believe. Thank you.
Image optimized to maximally activate a feature from layer 5. Corresponding maximally activating ImageNet. The image patchwise activation map. Feature from the last layer most activated by shopping carts.
So the first one in figure A looks to be some sort of pattern of circular multicolored objects.
Rocks. Or atoms.
Or spots of some sort. But the second image is definitely a salamander, and the final image is the mask of the object.
Yeah. This paper is only 7 pages long for the most part, and then it's just a bunch of stuff. A bunch of tests, like the layouts for the test and stuff. That's not bad. Alright, what's my analysis for this image? Yeah, a lot of rocky stuff. Then the center is... the echo's kind of bad. I hear myself every time I talk. The center corresponding maximally activating ImageNet example. Right. The image patchwise activation map. So when it thinks of a shopping cart, this is what it pops up in its head.
That has shopping cart features.
Yeah, definitely a lot of shopping cart patterns. Not a lot of good textures. Or maybe that's just the way it thinks of texture. I don't know. Like there's no green in the shopping cart.
A lot of strong diagonals.
Yeah, a lot of the like the middle handbar. It seems to think that's what a shopping cart is. There's no like really at the top of the image. There's a hexagonal structure. But other than that, there's not much.
There's a wheel and something that looks like the lower shelf, something that looks like the wire mesh on the sides. So there's spatial information there.
Yeah, that's pretty good.
And the final one is definitely some sort of mask, but I don't see how the last mask maps to a shopping cart.
It doesn't. It maps to the sprinkler thing.
Yeah, it does.
The mask in the first one is much better. Or whatever that is. Yeah, let's keep going.
Each of the above techniques can be formalized as follows. A fit represents each patch P of an input X at a layer A by an array A, L, P with D entries. We define a feature vector F to be a stack composed of one entry from each of these arrays. Let F, L, I be formed by concatenating the ith entry in A, LP for all patches P. This vector F will have a dimension equal to the number of patches. The optimization objective starts by maximizing the sum of the entries of F over inputs X. The main loss then is loss main for X, L, I equals the sum over P for FL, I, P dot. We employ total variation regularization by adding the term lambda TV x to the objective. TV represents the total variation, and lambda the hyperparameter controlling the strength of the regularization effect. We can ensemble augmentations of the inputs to further improve results. Let A define a distribution of augmentations to be applied to the input image X, and let A be sampled from uppercase A. To create a mini batch of inputs from a single image, we sample several augmentations, A sub K from A. Finally, the optimization problem is X star equals the argmax for X, the sum over K for the loss name for A sub K X, comma L, comma I, plus lambda TV for A sub K X. That is, they are regularizing over the loss in mini batches. And we're sampling several augmentations from A. We achieve the best visualizations when A is GS for CS jitter X, where GS denotes Gaussian smoothing and CS denotes color shift. Its formulas are Gaussian smoothing equals X plus epsilon, and epsilon is a number between 0 and 1, sampled between 0 and 1 randomly, and CS color shift equals sigma x plus mu. Mu is sampled out of the uniform distribution between -1 and 1. Sigma is sampled out of e to the u, sampled over -1 over 1. Note that even though epsilon and mu are both additive noise, they act on the input differently, since mu is applied per channel, that is, has dimension 3, and epsilon is applied per pixel. For more details on the hyperparameters, see Appendix B. To better understand the content of a visualized feature, we pair every visualization with images from ImageNet validation train set that most strongly activate the relevant feature. Moreover, we plot the feature's activation pattern by passing the most activating images through the network and show the resulting pattern of feature activations. Figure 3a is an example of such a visualization. From the leftmost panel, we hypothesize that this figure corresponds to gravel. The most activating image from the validation set middle contains a little lizard on a pebbly gravel road. Interesting, the gravel background lights up in the activation pattern right, while the lizard does not. The activation pattern in this example behaves like a saliency map, and we explore this phenomena across different layers of the network further in section 4. The model we adopt the majority of our demonstrations throughout the paper is VIT V16, implemented based on the work of Dozovsky.
Let's keep going.
2020. In addition, in the appendix, we conduct large-scale visualizations at a wide variety of variants, the ones named above, 38 models in total, to validate the effectiveness of our method. VIT 16b is comprised of 12 blocks, each consisting of multi-headed attention layers, followed by a projection layer for mixing attention heads, and finally followed by a position-wise feed-forward layer. For brevity, we henceforth refer to the position-wise feed-forward layer simply as the feed-forward layer. In this model, every patch is always represented by a vector of size 768, except in the feed-forward layer, which has a size of 3072, which is 4 times larger than the other layers. We first attempt to visualize features of the multi-headed attention layer, including visualization of the keys, queries, and values by performing activation maximization. We find that the visualized feed-forward layers are significantly more interpretable than other layers. We attribute this difficulty of visualizing other layers to the property that fits pack a tremendous amount of information into only 768 features, that is, in keys, queries, and values, which then behave similar to multimodal neurons. Due to many semantic concepts being encoded in a low-dimensional space. Furthermore, we find this behavior is more extreme in deeper layers. Figure 4 for the visualization of keys, queries, and values in both early and deep layers of the bit. And so figure 4, the top row are the keys, the middle row are the queries, and the bottom row are the values. And the columns are L1 and F0, L1, F1.
Huh. So the layers are in a single attention block. I think that's what they're talking about.
The F's are the feed-forward layer.
Oh, that's right. So that's a transformer block. A transformer block is an attention plus a feed forward. So this is the attention block. Or this is the transformer block, I mean.
The visualization both fails to extract interpretable feature and to distinguish between early and deep layers. High-frequency patterns and adversarial behavior dominate. And that's on the left. And on the right, the feed-forward layer. The first layer, linear layer, increases the dimension of the feature space, and the second one brings it back to its initial dimension. So my reading of that annotation suggests that there's supposed to be twice as many images there than there are. Because each column is labeled with an L1 and an F, and they're talking about separate L's and separate F's in the annotation. So I think this diagram is not correct, though it may not be that there's anything more to see in it than that.
All right, let's continue the feed forward.
Inspired by these observations, we visualize all features within the feed-forward layer across all 12 blocks of the bit. We refer to these blocks interchangeably as layers. The feed-forward layer, depicted in figure 5, takes an input of size d equals 768, projects it into a t equals 4 times higher dimensional space.
Where are you?
I am just below that.
Are you in the feed forward?
Yes, right where you have highlighted. And you'll want to scroll up a little bit so you can take a look at the figure 5 while I read them.
Yes.
Down a little bit, scroll down a little bit.
Yes.
The blue box is on the bottom of the page of figure 5, and we'll want to be looking at that while I'm reading. That's it. Yeah. The feed-forward layer depicted in figure 5 takes an input of size d equals 768, projects it into a t equals 4 times higher dimensional space, applies the nonlinearity GELU, and then projects back to d-dimensional space. Unless otherwise stated, we always visualize the output of the GELU layers in our experiments. We hypothesize that the network exploits these high-dimensional spaces to store relatively disentangled representations. On the other hand, compressing the features into a lower dimensional space may result in the jumbling of features, leading uninterpretable visualizations. And scroll down a little bit and I'll read figure 5. Does that figure 5 make sense to you?
Yeah, so they have a feed forward layer. It takes in a dimension of 768 and it projects it to a 4 times higher dimensional space, which is 768. I'm not that smart. 3072. Then it applies GELU then projects it back down to d-dimensional space, which is 76.8. It's basically like it's like a, how do you say it? It's like a elastic band that's like it's being stretched and then it's being recompressed. It's like a hair tie when you put it around your hair or like something. It's originally small and then it's expanded and then it contracts. On the other hand, compressing the features into a lower dimensional space may result in the jumbling of features, yielding uninterpretable
Why would they use
visuals.
a GALU here rather than a ReLU?
GALU is very nonlinear. Nonlinear.
Why would they want nonlinear?
Because nonlinearity leads to learning. GLU is used in almost every transformer. All transformers use GLUs.
So would this nonlinearity allow for this sort of stretching and compression?
No, that's done primarily with the dimensional spaces. The GLU's purpose is to just like kind of like some noise. Like kind of how like you know how like dropout basically allows the model to learn, or masking. That's like basically GLU's doing that. That's a good question though for further analysis.
Thank you.
But yeah, that's like best practice.
I did not know that. Thank you. I'm going to go on to section 4.
Oh,
Last layer token.
Let's analyze figure 5. So the 4 layer, the first linear layer increases the dimension of the feature space, and then the second one brings it back to its original dimension. This is a pretty good strategy for like any feed forward. Probably text. It takes in a 700. So the first layer is a linear. I don't know why it says FC1. That's just some convention people use, but it should be linear. Linear 1, linear 2, whatever. So the input chip is the BPD. I don't know what that is. What is BPD? Should be batch, pads, or patches, and dimension.
Yeah.
Yeah, so then it outputs patch or batch, patches, T. What is T?
T is 4.
That's right.
Expanding into 4.
4 times the dimension, which is 3072. Then GLU. Then second feed forward that takes the original shape of the output of FC1 and just transition it back to its original thing. And then this is added with the output of FC2 is added with the original input. And yeah, so something with feed forwards and transformer blocks, you're always going to have some weird adding operation at the end where you just kind of like add itself in the beginning. I don't know why. That also deserves deeper analysis.
So I thought that they did that because otherwise you run into getting off track, multiplication of errors, forgetting. And so this preserves the original context throughout the entire transformer model.
Perhaps. Yeah, let's keep going.
Okay. Last layer, token mixing. In this section, we investigate the preservation of patch-wise spatial information observed in the visualizations of patch-wise feature activation maps, which, as noted before, bear some similarity to saliency maps. Figure 3a demonstrates this phenomenon in layer 5, where the visualized feature is strongly activated for almost all rocky patches, but not for patches that include the lizard.
Mhm.
Additional examples can be seen in Figure 6 and in the appendix, where the activation maps approximately segment the image with respect to some relevant aspects of the image. We find it surprising that even though every patch can influence the representation of every other patch, these representations remain local, even for individual channels in deep layers in the network. While a similar finding for CNNs, whose neurons may have a limited receptive field, would be unsurprising. Even neurons in the first layer of a VIT have a complete receptive field. In other words, VITs learned to preserve spatial information despite lacking the inductive bias of CNNs. Spatial information in patches of deep layers has been explored in Raghu et al. 2021 through CKA similarity measure, and we further show that spatial information is in fact present in the individual channels. I don't know what the CKA similarity measure is, but that's fine. Let's take a look at Figure 6. Feature activation maps in internal layers can effectively segment the contents of an image with respect to a semantic concept. For each image triple, the visualization on the top shows the result of our method. The image on the bottom left is the most activating image from the validation set, and the image on the bottom right shows the activation pattern. So the one on the left looks like ocean, and the highlighty blue on the lower right. The second one is some sort of bottle.
Cylinders. I see
Cylinders.
abstract cylinders.
Abstract cylinders.
Mm-hmm.
Kind of like the base topological architecture of a cylinder.
Okay.
Then the third
and
is...
the lines there are interesting.
Yeah. Those are like reflections.
They're like yeah.
Because of the glass.
The next one almost looks like a swarm of fish.
Not really. It looks like faces. It's trying to formulate faces.
A crowd.
Yeah. That's
So
what
it's
it's
mapping the crowd.
Yeah. It's trying to create a bunch of faces. Well, that's what it's thinking.
Next one's trees.
Those look like trees. Actually, it doesn't look anything like in the original image. But they're trees. Not Christmas trees. Those look like a different type of tree. Or they're different from the clock tree. And then the fourth one looks like an alien monster. With a lot of eyes.
Very on top.
But that's a cake of some kind, strawberry cake or some cake object. The mask is pretty good, but still.
Yeah, it's activating for strawberries.
And then the last one looks like a bunch of sausages. But it's I don't know what that thing is called. It's a drum thing. I know people in my family used to have these things. I don't know what they're called.
Mariachi?
Yes. Yeah, they're fun. Alright, let's keep going.
The last layer of the network, however, departs from this behavior and instead appears to serve a role similar to average pooling. We include quantitative justification to support this claim in Appendix Section F. Figure 3b shows one example of our visualizations for a figure from the last layer that is activated by shopping carts. The activation pattern is fairly uniform across the image. For classification purposes, VITs use a fully connected layer applied only at the class token, the CLS token. It's possible that the network globalizes information in the last layer to ensure that the class token has access to the entire image. But because the class token is treated the same as every other patch by the transformer, this seems to be achieved by globalizing across all tokens. Interesting. Okay. Table 1. After the last layer, every patch contains the same information. Isolating class denotes the experiment where attention is only performed between patches before the final attention block, while patch average and patch maximum refer to the experiment in which the classification head is placed on top of individual patches without fine-tuning. What are we looking at now?
Oh, my thing. I found the code.
I found the code.
Yeah, of code.
Oh, good.
Yeah, I was just scrolling down for a bit, and
It
took me out, and now we're stuck with this massive downloading.
Yeah. And so the ability to dig into the feed-forward layers of a VIP is kind of useful, particularly when you're doing things like combining semantic and clip layers.
Mm-hmm.
So you want to do table 1?
What is the method?
What is the method?
So
Like what can we learn from this table?
What can we learn from this?
we're trying to figure out whether or not the isolating class in lower layers, I think that's what they mean by top. The classification head is placed on top of individual patches without fine-tuning. I'm not sure what that means. Do you know what that means?
What do you mean?
So they're saying isolating CLS is the experiment where attention is only performed between patches before the final attention block, while patch average and patch maximum refer to the experiment in which the classification head is placed on top of the individual patches without fine-tuning. I don't understand what that means.
So you have a patch, then attention is performed between the patches.
That's the normal way to do it, right?
Well, patch average and patch maximum. The classification head is placed on top of individual patches without fine-tuning.
That I don't know what that means.
So, classification head is placed on top of individual patches without fine-tuning. So that means the head of the classification. So, like, what is that saying? Is this like a donut? So the way you train a VIT is you have an image and then you have a classification. So like this would be a party. This would be the sky. That's what they're talking about. A classification head. You understand?
Yes.
So
But what does it mean that it's placed on top of an individual patch without fine-tuning?
so you have a patch and then you take patches. Patch 1, patch 2, patch 3. So for each patch you would have a classification. So you would say corner of a building, crowd, guitar. You understand?
Mm-hmm.
That's what that means.
Oh, okay. I think this might be something where I probably have to run the code.
Look, let me
But
show
that's
you.
fine.
So Fuyu does a good job of this.
Oh, I don't know Fuyu.
Fuyu is Adept, a model by Adept. There's not a paper. So look, this is a patch, right?
Yeah.
So what they're talking about, a classification head, would be a patch or like a classification. So you say this is an orange. This is an orange peel. This is an orange. This is what they're talking about. They're talking about the classifications for each patch. So this would be like white box with orange shape. So this would be like the classification for the entire image. They're talking about the patches. The classification head is the actual classification for each patch, not the whole image. So this is corner of an orange. This is orange peel. Corner of an orange. You understand?
Yeah.
Yeah.
Okay.
All right, let's keep going. Is everything good? Hello? Hello, Evelyn? Are you with me? Hello. Evelyn has gone away. Hello? Are you with us?
Sorry about that.
Yep. All right, let's continue.
Okay. The resulting hacked network that only has CLS access in the last layer can still successfully classify 78.61% of the ImageNet validation set as shown in Table 1. From this result, we conclude that the CLS token captures global information mostly at the last layer rather than building a global representation throughout the network. We perform a second experiment to show that this last layer globalization behavior is not exclusive to the CLS token, but actually occurs across every patch in the last layer. We take the fully connected layer trained to classify images on top of the CLS token, and without any fine-tuning or adaptation, we apply it to each patch one at a time. This setup still successfully classifies 75.75% of the validation set on average across the individual patches, and the patch with the maximum performance achieves 80.16% accuracy, further confirming that the last layer performs a token mixing operation so that all tokens contain roughly identical information. Figure 7 contains a heat map depicting the performance of this setup across spatial patches. This observation stands in stark contrast to the suggestions of Raghu et al. 2021 that VITs possess strong localization throughout the entire network, and their further hypothesis that the addition of global pooling is required for mixing tokens at the end of the network. Figure 8. Complexity of features versus depth in VIT-B32. Visualization suggests that VITs are similar to CNNs in that they show a feature progression from textures to parts to objects as we progress from shallow to deep features. We conclude by noting that the information structure of a VIT is remarkably similar to a CNN in the sense that the information is positionally encoded and preserved until the final layer. Furthermore, the final layer in VITs appear to behave as a learned global pooling operation that aggregates information from all patches, which is similar to its explicit average pooling counterpart in CNNs. And figure 7, heat map of the classification accuracy on the validation set when we apply the classification head trains that classify images on top of the CLS token to the other patches. So that's very smooth. There isn't anything that's standing out very strongly in that.
Not at all.
And so that's interesting. I was not expecting that behavior at all.
Yeah.
Comparison of VITs and CNNs. As extensive work has been done to understand the workings of convolutional networks, including similar feature visualization and image reconstruction techniques to those used here, we may be able to learn more about VIT behavior via direct comparison to CNNs. An important observation is that in CNNs, early layers recognize color, edges, and texture, while deeper layers pick out increasingly complex structures, eventually leading to entire objects, Ola et al. 2017. Visualization of features from different layers in a VIT, such as those in figures 1 and 8, reveal that VITs exhibit this kind of progressive specialization as well. On the other hand, we observe that there are also important differences between the way CNNs and VITs recognize images. In particular, we examine the reliance of VITs and CNNs on background and foreground image features using bounding boxes provided by ImageNet. We filtered the ImageNet 1K training images and only use those which are accompanied by bounding boxes. As several image objects are presented in image, we only take the bounding boxes corresponding to the true class label and ignore the additional bounding boxes. Figure 9b shows an example of an image invariance in which the background and foreground respectively are masked. And figure 9a displays an example of its ability to detect background information present in the ImageNet dataset. This particular feature appears responsible for recognizing the pairing of grass and snow. The rightmost panel indicates that this feature is solely activated by the background and not at all by the patches containing parts of the wolf.
So the grasses or like the snow is really well done. Like it actually understands the grass and the snow.
And the patch the mask looks like grass.
A little bit. It's still not there.
And so this is an example of the segmentation mapping.
Yeah.
Okay.
So, figure 9. VIT B16 detects background features. Image optimized to maximally activate a feature from layer 6. Center. Corresponding maximally activating example from ImageNet. Right. the ImageNet's patchwise activation layer. An example of the original image and masked out foreground and background.
So one of the things that is puzzling me is they've mentioned layers up to layer 10, and they've several times talked about gradually increasing aggregation of features, that is up to objects. But they're also talking about a semantic identification of the object based on the patches. Do you know whether or not VITs have been done with many more layers in an attempt to discover features that are even
Megavit.
more abstract than objects?
Megavit. Or actually, that's not what it's called, but Google made biggest fit ever. So they made scaling vision transformers to 22 billion parameters. So yeah. Yeah, so they did do this in 22 billion parameters. Which, I don't know if they have more layers for sure, but I mean, probably means they do. Yeah.
I'll have to take a look at that Google paper, because if they did add more layers, did they get more abstract in the lower layers?
Maybe.
Because it's a Google paper, no one's looked at the activations of the individual layers unless Google has.
Perhaps.
Well, Google doesn't normally release the weights of their models.
Yeah, they don't. They do not. Yeah. Excuse me. All right, let's keep going.
Thank you. To quantitatively assess each architecture's dependence on the different parts of the image in the dataset level, we mask out the foreground or background on a set of evaluation images using the ImageNet bounding boxes, and we measure the resulting change in top 5 accuracy. These tests are performed across a number of pre-trained VIT models, and we compare it to a set of common CNNs in Figure 2. Further results can be found in Figure 3, Table 3. Okay. Do you want to look at Table 2?
So they correlate background information with the correct class, which is the best model. Yeah, I did. VIT L16. Yeah, VIT L16 is the biggest. Why is it the best? Is it because it's the biggest? There's actually diminishing. There's diminishing returns in the patch size.
Diminishing returns in the patch size.
Oh no, the 16 is the resolution. Or it actually is the patch size.
So a smaller patch size is better than a larger patch size.
I don't know if that is the right correlation, but from what I can infer from the table, the best performing one is 16 patches.
I don't know what the L and the B mean in this.
So, I mean, yeah, that means... What does that mean? Looking at the bottle thing now. Large? I think it means large.
Okay.
Yeah, it means large.
We observe that VITs are significantly better than CNNs at using the background information in an image to identify the correct class. At the same time, VITs also suffer noticeably less from the removal of the background and thus seem to depend less on the background information to make their classification. A possible and likely confounding variable here is the imperfect separation of the background from the foreground in the ImageNet bounding box dataset. A rectangle containing a wolf in figure 9a, for example, would also contain a small amount of grass and snow at the wolf's feet. However, the foreground is typically contained entirely in a bounding box, so masking out the bounding box interiors is highly effective at removing the foreground. Because VITs are better equipped to make sense of background information, the leaked background may be useful for maintaining superior performance. Nonetheless, these results suggest that VITs consistently outperform CNNs when information, either foreground or background, is missing. Next, we study the role of texture in VIT predictions. To this end, we filter out high-frequency components from ImageNet test images via low-pass filtering. While the predictions of ResNets suffer greatly when high-frequency texture information is removed from their inputs, VITs are seemingly resilient. See figure 16 for the decay of accuracy of VIT and ResNet models as textural information is removed. 6. VITs with language model supervision. Recently, VITs have been used as a backbone to develop image classifiers trained with natural language supervision and contrastive learning techniques. These CLIP models are state-of-the-art in transfer learning to unseen datasets. The zero-shot ImageNet accuracy of these models is even competitive with traditionally trained ResNet 50 competitors. We compare the feature visualizations for VIT with and without CLIP training to study the effects of natural language supervision on the behavior of the transformer-based backbone. The training objective for CLIP models consists of matching the correct caption from a list of options with an input image in feature space. Intuitively, this procedure would require the network to extract features not only suitable for detecting nouns, that is, simple class labels like bird, but also modifying phrases like prepositions and epithets. Indeed, we observe several such features that are not present in VITs trained solely as image classifiers. And let's take a look at figure 10. Left, feature optimization shows sharp boundaries and maximally activating ImageNet examples contain distinct adjacent images. Middle, feature optimization and maximally activating ImageNet photos all show images from an elevated vantage point. Right? Feature optimization shows a crowd of people, but maximally activating images indicate that the repetition of objects is more relevant than the type object. Oh, that's interesting. Before and after and step by step, many. So that is a higher level of abstraction than an object. That is, many is not object.
Yeah.
Okay.
So figure 10 shows, or figure A, A shows the image optimized to maximally activate a feature in the fifth layer of a VIT clip to its highest activating examples from the ImageNet datasets. All three images share sharp boundaries, indicating this feature might be responsible for detecting caption text related to a progression of images. Examples include before and after, the airport images, or the adjective step-by-step for the iPod teardown. Figure 10b and Figure 10c depict visualizations from features which seem to detect the preposition from above and adjectives relating to a multitude of the same object. The presence of features that represents conceptual categories is another consequence of CLIP training. Unlike VitTrain, yeah, what were you gonna say?
So that explains better than the words what they meant by not only nouns. Okay, I understand that now. You want to keep reading, or shall I keep reading?
Yeah, keep going.
Okay. Presence of features that represent conceptual categories is another consequence of clip training. Unlike VITs trained as classifiers, in which features detect single objects or common background information, clip-trained VITs produce features in deeper layers activated by objects in clearly discernible conceptual categories. For example, the top left panel of Figure 11A shows a feature activated by what resembles skulls alongside tombstones. The corresponding 7 highly activating images from the dataset include other distinct objects such as bloody weapons, zombies, and skeletons. From a strictly visual point of view, these classes have very dissimilar attributes, indicating that this feature might be responsible for detecting components of an image broadly related to morbidity. In Figure 11B, we see the top leftmost panel shows a disco ball, and the corresponding images from the dataset contain boom boxes, speakers, a record player, audio recording equipment, and a performer. Again, these are visually distinct classes, yet they are all united by the concept of music. Given that the space of possible captions for images is substantially larger than the mere 1,000 classes in the ImageNet dataset, high-performing clip models understandably require higher-level organization for the objects they recognize. Moreover, the clip dataset is scraped from the internet, where captions are more often descriptive than simple class layers. And we're nearly done. Discussion. In order to dissect the inner workings of vision transformers, we introduce a framework for optimization-based feature visualization. We then identify which components of a VIT are most amenable to producing interpretable images, finding that the high-dimensional inner projection of the feed-forward layer is suitable, while the key query and value features of self-attention are not. Applying this framework to set features, we observe that VITs preserve spatial information of the patches, even for individual channels across all layers, with the exception of the last layer, indicating that the networks learn spatial relationships from scratch. We further show that the sudden disappearance of localization information in the last attention layer results from a learned token mixing behavior that resembles average pooling. In comparing CNNs and VITs, we find VITs make better use of background information and are able to make vastly superior predictions relative to CNNs when exposed only to image backgrounds, despite seemingly counterintuitive properties that VITs are not as sensitive as CNNs to the loss of high-frequency information, which one might expect to be critical for making effective use of background. We also conclude that the two architectures share a common property whereby earlier layers learn textual attributes, whereas deeper layers learn high-level object features or abstract concepts. Finally, we show that VITs trained with language model supervision learn more semantic and conceptual features rather than object-specific visual features as in typical classifiers. And there is another image. Okay.
Morbidity.
Features for
Music.
Morbidity and music. Yeah, that does look like a disco ball.
Yeah. Top left image in each category. Image optimized to maximally achieve a feature from layer 10. The rest 7 of the 10 ImageNet examples that most activate the feature.
What's the one in the lower right of music that kind of looks hexagonal?
If VIT was a human, it would be emitted for like super, super. I don't even know. Like it'd be have like 100 different mental diseases.
But yet, it's pretty good at making analogies.
Yeah, it is. It's still somewhat competent. This was a pretty good paper. Pretty good overview. There's still a lot. 33 pages
I
of.
learned quite a bit from this one. Thank you.
Yeah. Thanks. Yeah, they have 40 pages of visualizations of the layers. That's pretty insane. Yeah, these people took their time with this. Yeah, this is a good paper on like the history of like pretty good general understanding of just fit models in general. What's the state of the art? Why is it maybe the state of the art?
I'd like to read the clip paper after this.
Clip? Like the original clip?
The original clip paper. I haven't read that one, and I think for all of these vision transformer papers, it would help me make more sense of it.
Yeah, that would be. Or actually, the original VIT paper would be advisable.
Bradford 2012. 2021.
Yeah, so I think yeah, Clip is originally OpenAI. Yeah, that would be fun. I've been thinking about how to use fit models for like facial recognition. It would need to be extremely general and really fast. Like really, really, really fast. I don't know if it's possible, but I'm probably going to be working on that soon. Using a VIT for just facial recognition. I think facial recognition could be massively improved with some of this new state-of-the-art stuff. Because most of the facial recognition models are just really old convolutional nuts.
Are they?
Yeah.
Oh,
There's
I didn't know that.
There's not a lot of facial recognition models. Yeah, there's only 2 papers on the whole like VIT for facial stuff I found. Only 2.
So most often the facial recognition is attempting to match a face to an ID card or some sort of other physical token, like a badge or a password. So it's a classification problem. Does this face match the credential? It's not a who is this out of all people. And those are very different problem spaces. And I suspect that for matching a person to a credential, you could get away with very, very few features. Like
most of the facial recognition models are state of the art or in 2018. Not a lot.
How good are they?
Probably horrible. Yeah, killing 2 birds with 1 stone, efficient and robust training of face recognitions, convolutional neural nets.
I mean, there is another problem where you have images of people in public and you're attempting to match them against a group of faces of interest. And that's a much harder problem.
Maybe. Yeah, there's not been many new facial recognitions models. Convolution, max pooling. Yeah, there's a lot using just convolutional neural nets. Yeah, ideally you want a really small, like really fucking fast facial recognition model that can just analyze everything.
Well, faces anyway.
Yeah, but like, I mean, like all the details. I'm gonna try to implement, trying to get state of the art in a VIT for facial recognition. I think that'd be really.
That would be cool.
Yeah, but it has to match CNNs at speed, which is a problem because there is a tension, and that takes a long fucking time.
So V posted a link to a Mojo trial a couple days ago. And one of the things which was remarkable to me about it was Mojo, which uses SIMD, is fast on small models, but doesn't make any difference at all on larger models. So you have to keep the model within the RAM space of the device, whether or not it's your phone or the laptop or something else, or the GPU. But as soon as you go beyond that, as soon as you start getting into data swapping, SIMD does nothing. It just does not help at all. So if you can get a small model that does this, it will be fast.
Can you say that again?
So you want a model that's small enough to not require a lot of data shuttling in and out of the CPU or the GPU.
So what does that mean?
You want small patches. You want to keep the minimum amount of data to achieve the result. You don't want a really high resolution image. You don't want really high number of layers. If you can get away with using, if you could do it without splitting into 3 layers for colors, that would be helpful, because that is 1/4 as much data to be shuttling around. That is one image rather than 3 layers plus the final image. And if you can keep the data shuttling to a minimum, it will be small and fast.
It's a good idea. Mm. Also, this could be a pretty good product. Like a really
Yeah, it's a great
fast,
product.
really fast facial recognition system for maybe like government, like police, or like, I don't know.
Now, the problem for government and police is very different than the problem of recognizing is this a friend or family versus a stranger. That's a simple problem because you have many examples of the family or friend. You have, and when you get something that doesn't match the common example, then you know they're a stranger. But on the government side, you have a problem of needing to match a whole bunch of individuals accurately, many of whom you haven't seen recently. And so you want to match against a credential because they're going to present a physical or digital token that says, this is me. And so it's a matching between those two. And the police problem is different again. I'm looking for this person in a crowd. There are half a dozen people that look sort of like this person, and I don't know if this person is even there. Very different problems.
Yeah.
I think the family or stranger, easy problem. I think the matching against a credential, fairly easy. I think the finding a stranger in a crowd, pretty hard.
Yeah, that might be that's a good thing to think about.
Happy Halloween, Kai. This was delightful.
Thanks. That warms my heart.
And I will be thinking of all of the dead tomorrow.
That's good. Because if you
Good
didn't,
night, Kai.
they'd probably be lonely. They'll be very grateful for you. Thanks
Good
for your
night.
time, everyone. Have a lovely one.
Thank you, Kai. I hope you sleep well.
Thanks. And that, my friends, concludes tonight's paper evening. This is the first time I'm speaking to you. Yeah, you. How you doing? I'm Kai. I make Neural Nuts, and every night at 10 p.m. New York time, we host a paper club, and we review some papers. Some AI research papers. We talk about, what's state of the art, what's not state of the art. We talk about how things work a lot. That's primarily our focus when we read a paper. The method. Experimentations are important, and we've been trying to dive deeper into those. But we really focus a lot on the method. How are things getting done? How does that lead to outcomes people actually want? Are those outcomes actually real? Are they benchmarks? Are they accurate? Are they general? Are they fast? We love taking these things into account in our analysis. Well, thanks for your time, and stick around till tomorrow. Thanks.